Dear friends, dear colleagues, welcome to our seminar. It is my pleasure to introduce our speaker today. It's Michael Hintermüller from University of Berlin and the Weierstrass Institute in Berlin. Michael received his PhD from the University of Linz and his habilitation in mathematics from the University of Graz. After spending 1 year at the University of Sussex, he received an offer from the University of Berlin, Humboldt University, and became 2008 professor in applied mathematics there. And since 2016, he's the director of the prestigious Weierstrass Institute for Applied Analysis and Stochastics in Berlin. He's science fellow. He's a spokesman of the Einstein Center. He's a spokesman of the Berlin Med Research Center, MedPlus. So Michael is involved in many activities as a scientist and, if I'm allowed to say, as a politician. So it is our great pleasure to have him here today. Michael, the floor is yours.
All right, thank you very much, Rado, for this kind introduction. I'm not so sure about the politician. This is hopefully an image which I don't have, and I don't hope that you take this from this talk today. But let me first, of course, thank Rado and his co-organizers for giving me this opportunity to speak in this One World seminar, which is indeed a very good invention in this very difficult period. We just spoke a bit about vaccines and the programs. I think slowly but surely we are coming back to more regular terms, and certainly I hope to see many of you at one or the other meeting in the future in person rather than just electronically. But I find also the electronic seminars and talks and discussions have come quite far. So in that sense, I hope I'll do a good job today with this seminar. If there's anything in between, feel free to interrupt me. Otherwise, I'm happy to share slides, also give you pointers to a preprint and so on and so forth. So I'll talk today about something which we came across recently, also a bit influenced by this intensive research and learning, machine learning models, which we see in many areas arising, also in many applications. We'll have a look at this within optimization of differential equations and specific applications in mind. And let me also say that the work is joint work with two postdocs of mine. One is Guo Zidong and the other one is Kostas Papafitsaros. Now, let me see. I can get, yeah. So I would start with a very general slide. I mean, what we see very often, of course, is that we collect from inputs, outputs. This could be, outputs could be certain observations given certain input parameters or scenarios or design quantities. And then, of course, very often our task is to find a model in between. You either have a purely physics-based model or you use your data in order to find a data-driven or data-based model, which it would then use for prediction in many ways. It could be analytically, could be numerically, could be also in other ways. And I would use the term ab initio models for those models which are informed by basic principles from physics. Typically, for instance, this application field giving rise to partial differential equations or differential equations in general. And then, of course, very often there are also some components which come from data, and then you have specific aspects of bringing in data. So these models are very often a compromise, and of course we are on a strive to make those models more accurate, but sometimes available at all, because there could be models which are not accessible directly by ab initio type considerations, but rather through data only. And in this context, of course, we have learned that neural networks, in particular artificial neural networks I'm talking about, are efficient tools now to learn such physical laws from data only. Of course, we have to debate to what extent we can learn complex models, but I'll give you some glimpse on what we believe can be done in a meaningful way also within optimization. And of course, by doing so, we take advantage of not only available data, but also computational power, because very often the models which you would then have at hand are no longer sort of analytic models, but rather models through some algorithms or through some software and so on and so forth. Now, let me be a bit more specific and look towards optimization. And let me also introduce some notation here. So I would call inputs or designs or controls UI, and let's assume we have capital N, many of those. And let's assume that these kind of scenarios UI, for each UI, generate an output yi, and so I have capital N many outputs yi. And let's assume in between there is a partially unknown physical process, and the mapping from u onto y will be called capital pi. And what we shall see in this talk is now the fact that we are going to replace this pi by a learning informed model, which you can see in the blue box in the middle here. You can see my little pointer hand there. So notice that the pi is replaced by pi sub n, indicating that some network-based approximation is underneath. And there are several ways how it could be influencing the pi, and I'll give you two specific ones throughout the talk. And then, of course, such a mapping of a control u onto a state y would work, for instance, as a side constraint in an optimization framework, which is here rather general, I would say. It could even be yet more general by also learning other quantities. But what you see here is you wish to optimize with respect to y's and u's. Let me call the y's already states and the u's controls. So you have a state control pair, which could be functions, obviously. And then you have to minimize some objective. What we see often in inverse problems or in control, a so-called tracking type objective. I have a kind of output operator A, which leads you into some measurement space where you have some measurement for observation G, which you wish to track in some Hilbert space H, say. And then you have a price to pay for having a control, or you have to regularize the problem, and the price is alpha positive, and you have a certain control space, capital U. The controls U could also be confined by C admissible, and then of course there's a relation U between U and Y given by pi n. This is what I'll focus on in particular. So the talk is also inspired by two applications. Number one, for instance, is one coming from phase separation, where we like to learn a specific constituent in a partial differential equation and then take advantage of knowing how the solution process for the PDE works, either analytically or also numerically by having some software at hand. This is the left-hand picture, which you see a kind of phase separation profile here between two phases, a black and a white phase, which could be, for instance, binary alloys, two different alloys in a kind of phase separation process, which over time starts from maybe a homogeneous mixture and then separates the phases into one or the other metal, so to speak. Could also be more complicated where you have fluid dynamics sitting inside, but this is not necessarily the focus, making the problem more complex. The second example which I have in mind comes from image processing, where I emphasize the word quantitative magnetic resonance imaging. Quantitative means that you wouldn't like just to look at a nice looking image, so to speak, which would be rather qualitative information, but you wish to assign to the involved tissue, which you can see here color coded, specific sort of absolute values, in a sense that a specific value would indicate a specific tissue. And this makes the image then quantitative, which is of course information which we need in order to use this image later on for other potential machine learning tasks. For the second application, we shall see an application where we try to learn the whole solution operator from U to N to Y, and not just a map inside the partial differential equation, which gives then rise to pi n. I'll be more specific in a second. Let me just give you a little bit of an outline of the remainder of the talk. I'll quickly review a few aspects of deep learning. I'm sure you know more than I do about this, so I'll just give you a few glimpses of this and the current state. And then I'll go into this model problem again, give some general results, and then two case studies along the lines as just indicated, one in phase separation and the other one in image processing. And finally, I'll conclude. Now, mathematics of deep learning. I mean, I realize such a statement is now, such a title is very dangerous because this is a very rapidly ongoing field right now. And as soon as you talk about it, you might already be outdated because there's a new result around. But at least I would like to set the stage a bit about neural networks as we use them in this context of the talk here. And I'm sure you have seen such an image, such a graph on the upper left in this or different formats in several talks in the recent past, where you have several layers of an artificial neural network. You have an input layer depicted in yellow. Then you have neurons going from the input layer to the next internal layer, which is the first green layer. And then you have many other neurons connecting to the next layer and the next layer, and then there's an output layer. So I'm emphasizing here that the input layer and the output layer don't need to have the same size, but also this is not well done here. The hidden layers could have different sizes as well. It looks the same all the time, but it's not necessarily the case. And let me also introduce a bit of terminology. Again, my U is an input variable, Y is an output variable, and then I go from layer to layer by using a kind of transform, so to speak. So I have an input quantity, which I call HL on the lth layer, which I finally transform into some W sub L HL plus BL. And then I have to decide on whether the next neuron will be activated or the next node will be activated or not. And this is done by an activation function sigma. I'll give you some examples on the next slide. And then you repeat this process on the next layer. Now you have generated an HL plus 1, and you repeat this affine transformation and activation functions until you have marched through the whole system, and in this kind of feed forward idea here. And finally, I have written it down just for the one hidden layer case. You would start here with the U, get the first affine transformation, you do the activation, you transform once again, and this is what gives rise to the output Y. And the mapping from the initial to the final stage would be this curly N. And of course, you can see how it works in case you have several layers. And of course, you also notice that the matrices W and also the shift vectors can change in size depending on the specific layers. And then, of course, the task is given certain measurement data. I indicated some pairs UJ, YJ initially. You wish now to do the following. Within W and the B's, you have all these unknown components sitting, which you wish to determine by the data UI or UJ, YJ through minimizing an objective functional, which would then very often consist, see how to march back. Not so easy now. No. Yeah. Which you wish to minimize then. So there could be some data fit term. This is the delta in the first part, and there could be some a priori decisions or regularization terms, which are the little r's here on the second part. There could be additional constraints hidden in this F admissible there, and this is a problem to be solved. So this is a complicated problem in its own right, but not the focus of this talk. So let's assume we have solved this problem already, and we get a neural network approximation curly N through data pairs UJ, YJ. Now, what do we have at hand in terms of approximation results? Several, and I'll just cite two, which go back to work by Pincus in Acta Numerica at the end of the 90s. And if your F operates on a bounded set omega, for instance, into Rn, and the bounded set is again a subset of some Rm, then unless your activation functions are polynomials, you can get accuracy to any degree. So in a sense, you will find to any continuous function, a neural network approximating to any degree of accuracy, unless the activation function is a polynomial. And you can also have the same statement. This is what the second theorem does here for the derivative. And of course, this could go on if you have enough regularity in your whole system, so that you can also not only approximate the function, but also derivatives in a kind of uniform way through this universal approximation results. Of course, I realize that people are now currently working on different types of approximations, also connected, for instance, to partial differential equations, Sobolev regularity, and things like this. This will also be useful and can be built into this research in the future, but they're not our current focus here. Now, I talked a bit about activation function. Just to be a bit precise, we can maybe distinguish the world here between two halves. One is the smooth and the other one is the non-smooth one. Very often we see smooth to activation functions like the ones which I have depicted here, the sigmoidal functions in the upper bullet, or the probabilistic functions like the softmax in the second bullet. And they are sort of contrasted by non-smooth activation functions like the rectified linear unit function, which is used very frequently. It works very well. In particular, it sparsifies networks quite neatly, but it comes at the price of being non-smooth. And this non-smoothness, of course, changes this learning problem. Of course, not only the learning problem, but it also changes the N map which you receive. It will be a non-smooth map, because remember, it's a kind of superposition of affine transformations, activations, affine transformations, and so on and so forth. And if I replace now my pi n by an n which is smooth versus an n which is non-smooth, of course, we enter, in a sense, two different areas of optimization, if you wish. So for the disappointment of at least half of you, I realize I'll go the smooth path today, although many of you know me that I usually rather like to be on the non-smooth side of the universe. Now, what do we know somehow about the general settings? I mean, I have given a universal approximation theory pretty much fitting into this bullet or item number 1 here, where we have F mapping from a finite dimensional subset into some finite dimensional space. You can use universal approximation, and a specific application which we see very often is generalized regression for finding such a mapping F. But as soon as or infinite dimensionality comes into play, like in item 2, 3, and 4, things are not as well researched as for 1. And in some cases, like in 4, there's very little research, but there's already some research going on, but this should be still complemented by many more efforts. So what are the differences? In the second case, we map from an infinite dimensional space into Rn. This is something we see, for instance, in the context of image classification. Here you map from some Banach space into Rn, and mostly done by convolutionary neural networks. And there is quite something known, but still this is under development. Same would be true if you try to use neural networks to approximate solution of partial differential equations, a bit leisurely written here as a mapping F from omega into some Banach space P2 here. Very often this would be specific Sobolev spaces fitting the partial differential equation theory. For instance, if you think about approaches like physics-informed neural networks, then this would be some way of how to approximate the solution of a PDE by a neural network-based discretization, which has advantages, but of course it also has the disadvantages like non-locality, but also certain non-convexity and things like this. And the last one might be the most interesting one mathematically, because it's, at least to my opinion, quite open right now, that you try to learn operators between two infinite dimensional spaces. So this example fits a bit my second motivating case of quantitative MRI. And one of the main difficulties, as you may imagine, of course, is always this kind of compactness and boundedness condition, as we've seen it in your universal approximation result. And this complication comes, of course, as soon as we have to deal with infinite dimensions and the usual difficulties there. Now, I wish also like to clarify some terminology before we get into some details here. Because there is this notion of physics-informed learning versus learning-informed physics. It's not necessarily the same. My understanding of physics-informed learning goes back to some work, as we have seen it in this item number 2 here, by Rassi, Berdikaris, and Kariniadakis in JCP 2019, where a physics model enters the learning. So then the loss function, which was the delta, remember, is not just some data fidelity in a general sense, but it would be the PDE or the differential equation residual, which then informs the training process in a sense by the physics modeled into the PDE. And this is usually this item 3 on my previous list, where you go from some domain omega into some function f, which would be then defined over omega, but it would be considered as a function of some Sobolev space. On the other hand, learning informed physics is something else. It tries to use an artificial neural network to predict physical models or specific constituents of physical models. Then you can still have general loss functions, regularization functions for the learning process. So it doesn't necessarily need to be the PDE residual, but very often it gives rise to mappings between two infinite dimensional spaces in the sense of learning solution maps of differential or partial differential equation equations. So we'll focus on the latter one, the learning informed physics, as this is what I tried to motivate in the previous slides. Now I'll come to my model. As we have seen it in this right green box on my second slide, I'm focusing on a specific objective function here, but this is not the key point. You can also generalize it as long as you have some reasonable assumptions concerning allowing for existence and other aspects. You have an equation here modeled abstractly by some mapping E, and this is what I call the physical or the physics model. It could be an ODE or a PDE, and connects the control U to the state Y. And I consider also the U to be confined to some admissible set, C admissible, Could be the entire space, but doesn't need to be the case. For instance, in the image processing, this could be a range of physiological relevant parameters, and they are typically confined to certain ranges and not free in space. We assume well postness of the PDE, at least locally. So that means given a mapping, given a point U, you can locally resolve the PDE to get back an implicit map pi, so that Y locally is the pi of U. Excuse me. And then the idea, as I outlined on the second slide, is to replace this map pi now by pi n. And this can be done in different ways. And what I would have in mind would be, first of all, let's just focus on the two different ways, which I'll look at. One is I have a PDE which has some constituents which I strongly believe in, but it has some constituents which I need to learn from data. But then the overall solution process is not an unknown, it's something which I know as well. So which means I just learn a constituent within the PDE, and then the pi n is a composition of this learning, this one's constituent plus applying some known solution method to the PDE problem or ODE type problem. And the second example is a bit different. It says I just have input-output pairs. I don't even have an idea about the ODE or PD and try to learn the map from controls to states right away. It's a bit like learning the entire solution map for a PDE. But as you can imagine, if the system is too complex in certain aspects, then this is a delicate task, and we shouldn't expect that machine learning can solve this all the way, but at least in certain settings it can, and I'll give you one example. And there are many questions to be asked and many questions to be answered. One of the questions, of course, you might have in mind is what are conditions for well-postness of the learning in physics, of the learning informed model? What about approximation theory in terms of the system, but also in terms of the optimizers resulting from such a minimization task? And of course, you could think about many other aspects in the approximation of not just the optimizers, but also adjoints and so on and so forth. Now, first result is an existence result. If I call Q now the superposition of solving the PDE, I get the mapping pi, and then applying this output map A in the objective, this would be my Q. Then if the Q is weakly sequentially closed, meaning if you have a weakly convergent subsequence or sequence UN in space U to some U, and the QUN converges to some G bar in the corresponding space H, which fits the objective functional, then the G bar would indeed be the Q at U at the weak limit U. Under this assumption, you have an existence of a solution U bar, and you can work around a little. For instance, if you have a situation where the C admissible is a bounded set and belongs to a subspace U hat, which is compactly embedded, because then strong and weak sequential closeness of Q would be enough. I'm mentioning this here, the latter one, because for many PDE models, you have a certain gain in regularity, and then you can somehow conclude or infer such a strong weak principle rather than a weak principle. And also this compact embedding fits well the context of inverse problems, where sometimes the alpha term, remember alpha over 2 norm U squared, is used in order to regularize also in the space of functions, and then you may have some compact embedding arising from there, which gives rise to the second part of this proposition. Now, what do we know about approximation? I'll now call Q sub n the operator arising when I have, let's say, several neural networks, n sub n, which give rise to some mapping pi n in what sense ever. And A is again this output operator. Then we can decide when we have the situation that both are weakly sequentially closed, Q and Qn for every n. And I have some locality assumption on the admissible set C admissible for U. That's what this assumption does here with the epsilon n's inside. So which means for all U which are feasible, Q and Qn are close to each other in this very sense here. And if epsilon n goes to 0 for n to infinity, which would mean I improve my approximations of the neural network in one way or another, then again, I get convergence, a sort of consistency result that I have, first of all, existence of a solution for the UNs, UNs for the problems where I have the QNs, And as n goes to infinity, this sequence of un would converge strongly to u bar in u, and u bar is a minimizer of the original problem, and also this output map in this Q would have a convergence correspondingly strongly in H.
But Michael, one question.
Yes.
So UN would be global minimizers, I guess.
UN would be here in this little example. It would be a global minimizer because I assume that I can globally resolve. You can of course also confine this to some locality around the point, but this makes the presentation a bit more technical. But otherwise, for simplicity, think about global minimizers. That's a good point.
But then the problem is still non-convex, I guess.
The problem might still be non-convex. So this is why I'm saying you could also confine yourself to local minimizers here, and this would still be fine. In particular, I'll show you an example where we have a non-convexity, which is immediately the case whenever you control a PDE where some nonlinearity is inside the PDE, even if the nonlinearity would be monotone, the solution map, reducing the optimization problem may give rise to some non-convexity there. But you need certain assumptions for compactness. But otherwise, think about the local version of this result. Now, what else can we say about rates of approximation? Well, here we have to introduce Lipschitz constants L0 and L1 here, which belong L0 to Q and L1 to Q prime. And I call the distance between Q prime and Qn prime in the corresponding operator norm eta sub n. And then under some smallness assumption of L0 and L1, the solutions UN converge to some U bar, and the rate is as shown in this first theorem here. You can see on the one hand side, the approximation quality of the mappings Q themselves, weighted by L0 plus a kind of residual term weighted by eta n. It's interesting to display the residual term because sometimes you're lucky and you have a zero residual problem, which honestly is not very often the case, but sometimes it is. And if you have a zero residual problem, which means QU bar indeed equals G, then obviously you only get the first part of this estimate. And the capital O is the usual notion for there exists a constant, so that this is less equal to constant time L0 times epsilon n and so on and so forth. On the other hand, it might also make sense to look at the case where you don't have control constraints, which means C admissible is not active or it's the whole space. This is when the reduced objective J prime, this curly J, remember, comes from reducing the problem we have not even shown you. Let me just go back. So the curly J emerges, here's the Jn, but before we had the J, the curly J, it emerges whenever you reduce the problem by resolving the PDE through the solution map. And this is, of course, where you either have a locality or global approximation. What the curly J is this reduced objective, as we call it. And the J sub n is the corresponding network-based one. Now, if the reduced objective has zero derivative at U bar, which means the constraints are not active or simply not there, then it turns out that the condition on the Lipschitz constant can be a little bit simplified, but you can see that the size of L1 is weighted by the residual of the matching term, and it has to be balanced against alpha, which is the cost of the control term. And this is what I mean by smallness of L1. And in the first case of the first theorem with L0, this is even more confining to some extent. Then you have that UN minus U bar is capital O of the square root term here. Again, you can see there's the same orders type term, and you could even spell out the constants in a bit more details than similar to above. But otherwise, you can see that there's a different kind of approximation in terms of the order there. Now, case studies. Let me go into these two case studies and let me look at the first example where I have the following assumption. Let's focus on the subject 2 line first in the problem above. So we are minimizing objective. Again, if you don't like to see the quadratics, there are other ways of putting an objective there, but we can very often see the quadratic there as a tracking type term, which fits a control context or some local approximation of the problem. where I have a quadratic approximation, then in the objective, and so on and so forth. But now let's assume you have some ab initio modeling minus Laplace y, which you believe in. So there's a diffusion term which you believe is sound. You know how the control enters the process of the design variable here in my simple setting just via the right-hand side. But let's assume you're not sure about the curly f here. So it's not completely known and you wish to infer it from data. And you may say, I'm either correcting a model which I trust, which is the PDE without the blue F, or you say, I have to learn a quantity from scratch because I don't know what to put in there. And this is the underlying thought here. You have a certain boundary condition here. I have a Neumann boundary condition on the boundary of the PDE domain omega. And I have constraints on the control here, simple box constraints, but again, this could be other types of constraints if you wish. And the goal is now to learn the control to state map pi, which maps the control u onto y. And I guess now you see what I meant before when I say you learn a constituent. This would be the f, but the solution map for the PDE in its own right is just the classical, let's say, Green's formula technique, or you say I have in the discrete world a solver which manufactures a solution if I implant an f or a learned quantity of f. So this is then giving rise to the pi n map. So in a sense, that's what I just said. You now wish to learn f through a neural network, n replace f by n here, and that's the model which you really have for your optimization. And of course, there would also be nice ways of thinking how to intertwine in the solution world a solution process for this control problem with the solution process to find n. This can be done in a clever way, but again, not focus of this talk, but certainly an interesting aspect for future work there. So let's nevertheless assume some things on F, despite maybe us not knowing, but we have to assume that the underlying physical law, which we have to more or less discover, has certain properties. It's a bit technical to go through this in detail. The bottom line is the assumptions on little f should do the following. They should give rise to a so-called Karadzic map. And secondly, they should enable an Nemitsky operator. So the first part on regularity more or less gears towards Karadzic, which is measurability in the first component and some continuity in the second component. You have a growth condition for the f, which is needed for existence for the underlying PDE. And this also involves the existence of a primitive function f, which allows us to connect capital F, which allows us to connect the PDE problem to an energy minimization, as we shall see. Coercivity, this is what we need for guaranteeing existence of this capital F function, and also boundedness from below in order to enable a kind of informal sequence argument for existence. To the following problem, let's have a look at this capital G of y problem, where we have the first part with the gradient y squared in the L2 norm, plus our primitive of the little f, the capital F function, minus integral over u times y, and we minimize over y in H1. Then we can, in general, this is delicate, obviously, because we have said nothing about convexity or so of the capital F function. But we have other properties in place so that whenever we know that u is in LR and r is larger than p over p minus 1, which is a dimension dependent Hölder exponent p there. I wouldn't want to go into more details here. At least I want to indicate the typical L2 regularity might not be enough then the optimization problem admits a solution in H1 which satisfies its Euler-Lagrange system, and the Euler-Lagrange system precisely is negative Laplacian y plus little f of x comma y equals u with the Neumann boundary condition, which is our constraint PDE as we indicated above. You can also get some other results which are useful from Nemitsky type operator considerations, where whenever the box C admissible or the constraint set C admissible is in L infinity bounded, then you can show that the state y is bounded not only in the H1 norm, but also in the continuous functions over the closure of omega bar, which means there is such a constant. And this is, of course, important if you think about our universal approximation results, because we are going to have our little f function. We plug into the little f an x, which goes which comes from omega. Let's assume that the PD domain is bounded. Then we plug in a y of x, and if the y in the continuous function satisfies such a bound, then over omega bar, the y of x is bounded as well, and we operate now on a bounded set with our mapping F and can use universal approximation results. So what we do here in the first instance, I realize I have to be much quicker now. In the first instance is that we wonder, what do we know about solvability of the PDE? And the first with the learning informed constituent. And the first answer is, well, if I want to be epsilon close to F with my neural network function N, then there indeed exists such a neural network with smooth activation functions, so that there is a solution to this learning informed partial differential equation. And more or less, this is an interesting result using this universal approximation result and the fact that in C over omega bar or L infinity of omega, we have this bound K. And this gives rise to considering now F or the approximation N on a bounded set only with respect to the arguments. We have further properties because we need to work towards a KKT type system. So we look at continuity properties, and under certain assumptions on the negative part of the partial y of f at some reference point y naught, you get this kind of local Lipschitz property as you would expect in general, but one has to be a bit careful here, obviously, because we're inserting the neural network-based operator n there. And you also get the directional differentiability result by dividing yn minus y naught over by tn. You get existence of a weak cluster point P here, which satisfies a linearized PDE, which you can see down there in the middle with the perturbation H there, normal boundary conditions, and you get the corresponding result. There's parentheses missing. Corresponding boundedness result as you would expect it from these types of PDEs. Okay, now what is interesting about this locality assumption, so remember we need a universal approximation. For the universal approximation result is boundedness. What I'm showing you here is a typical little f function here, which comes from a double well type potential. And as I indicated it down there, so this is a derivative of a double well, which is this y to the third minus y term. And as you can see, the neural network approximation does not approximate very well globally. But in technical details, this doesn't matter that much because, for instance, for these very applications, the range y from -1 to 1 is of particular interest because that's the physical relevant range. For instance, if you think about concentrations of substances, where substance A is -1 and substance B is concentration 1, then the range between -1 and 1 means a mixed state. So being far outside -1 and 1 has no physical meaning, and still the neural network approximation does very well in a certain neighborhood of 0, which is sufficient for our purposes, for instance. This gives you a glimpse on the double well potential as we've used it in our computations. And let me move forward. I'll show you also some results later on the optimization process. But before I do so, let's say some words about directional derivatives, which are then used in the context of the adjoint calculation. Again, if you have an epsilon approximation, want to have an epsilon approximation, then the universal approximation theory gives you existence of a network. You don't know how it looks like, but you know that there is one, such that you get epsilon close. And from this, you get further error bounds as indicated down there for the states y and yn. This is the blue line, the first blue line, and then also for the corresponding directional derivative or adjoints p and p epsilon here down there. And again, you can identify certain rates under an assumption for the derivative of f in the neural network map, which you have at hand under the assumption that the neural network is a smooth one. Okay, I think I'll be very brief. I don't explain how we solve it numerically, but in a nutshell, if you write down the KKT system that's using a linear complementarity-based function for box constraints, that's how it looks like. You may want to apply non-smooth Newton right away. It has some drawbacks in terms of globalization. but it seemed to work very well. But what we rather did is we used the kind of semi-smooth Newton type SQP method, where you set up the usual SQP problem, as you see it down there, solve the SQP problem by semi-smooth Newton method, which is very efficient and even mesh independent in this context. Then you do a line search procedure, update and iterate. And for the line search, we use an exact penalty or exact line search, and inexact solves for the QP sub problem, and the inexactness was more or less tuned by the decay needed for the line search process. So you needed a descent direction so that you have a certain progress in optimization. This can be exploited when allowing some inexactness. What you can see here are now the results. The left column is the learning informed, and the middle one is if you would have an exact PDE. And you can see these phase fields, black and white, and this red and yellow phase in between is the transition from -1 to 1, if you wish. So you have in black one material, in white the second material, and in between you have a transition, which should be grayscale, but for visualization purposes, we did color coded here. And you can see from the error maps that the learning informed model does quite well in terms of approximation. This is what you see on the right-hand side with respect to the true physics informed model. We used a very moderate network size and probed a bit with how many layers. We did 1, 3, and 5 layers with a small, medium, and large degree of freedom. Made some observations, but for some medium size, you get already this result here, which was about 300 unknowns for the learning problem. Okay, let me finish off by looking at the second applications. What I've shown you in the first case study is to learn a constituent in an underlying law, which you then complement by solution process, which is more or less exact or known from numerics for this specific law. Now, in my second application, I try to look at an image processing task where I try to learn the entire solution map, the whole pie, not just the constituent, but the whole map. Now, maybe I do not go into the details of MRI, but what you see up there is one model for the physics, which is a so-called Bloch equation. It's applied voxel-wise or pixel-wise in a 2 or 3D context, where Y would be a magnetization over time, B some external magnetic field, G is some constant there. And the interesting quantities here are, so Y is vectorial, as you can see, with 3 components in 3D space. But the interesting quantities here are T1 and T2 because they are so-called longitudinal and transversal relaxation times in an MRI experiment. And those are the so-called quantitative parameters, which are more or less unique to the tissue. And out of a magnetization result, you wish now to identify the tissue-related parameter in order to make the reconstruction process quantitative rather than qualitative only. And this gives you some idea how an ideal T1 map looks like in the left plot, an ideal T2 map looks like on the right plot for a brain image, and the rho is a proton density, which appears also in this equation on the right-hand side, which is again a quantitative parameter. So again, a reconstruction would only be quantitative if you do not try to aim just for Y, but if you try to aim for T1 and T2 because they are unique with respect to the underlying tissue, and those are the quantities of interest there. So having said this, you may imagine that our design or our interesting parameters are T1, T2, and rho. The proton density, as you can see down there. The state Y is indeed the Y which comes out of the Bloch equation, and you have some initial conditions and also some physiological constraints for these parameters, depending on the region of inspection there. And what you see in the upper level objective there, and up there is the following. You have Y, which is the magnetization, being fully transformed by curly F into so-called K space. And then you do some subsampling through the operator P. So this makes the problem now a bit challenging. So this is a kind of inverse problems to be solved here, given some data G delta in which are subsampled in this kind of K space. And alpha norm U squared really serves the purpose of a regularization term. This would be the ideal world, but let's assume we do not know the physical law in there, but rather have data pairs UI, YJ, YI at hand, and we try to learn now the map from U onto Y. And this is what we are about to do here. So we're not just replacing a single constituent in the ODE and then use the ODE solution technique, but rather we do a full operator learning here. Admittedly, and this is a bit swept under the rug here for a time discrete sequence here, because the MRI experiments have specific pulse frequencies there, and these frequencies give rise to a time discretization of this type of Bloch equation. This is underlying this operator n here. I think in the interest of time, maybe I'm not walking you through the details now, because I realize I should stop soon. But of course, we now more or less complete a similar task. We ask ourselves for a feed-forward network. This is what we do here, so residual feed type network, which you can see down there, mimicking somewhat a time discretization of an ODE, explicit in time if you wish. We again have the similar observations as before. We can find, given some reference point U with a map pi, a neural network n, such that the operator pi n is epsilon close to the corresponding operator pi in the right norm here. And the same is true for the derivative. Again, we use a smooth neural network there, maybe 2 different approximation levels. This is a kind of, again, state matching result, which gets arbitrarily good depending on the network. Again, it's not constructive, but at least this is an existence result. And then we apply the very same SQP algorithm as before with a specific approximation for the hash. And I think I don't need to tell this in this audience here in detail, but I'm happy to talk about this afterwards. And this is just the first glimpse into these results, again, at the moderate size with about 300 unknowns for the neural network training, corresponding data. You can see in the bottom line, the learning-based reconstruction for T1 and T2 in a row, and you can see in the upper row, the ab initio physics integrated method, if you believe into the Bloch equation. And it's maybe difficult to see the quantitative comparison, but at least if you do some further analysis, you would see that the learning informed model is not worse than some ab initio consideration, even with respect to the true data to be assumed. Yeah, so in this sense, this gives us quite some hope that also learning the operator can be done. But again, note, this was not learning a PDE, a complex one, it was learning an ODE of a specific structure. And this is why I guess it also worked so well with reasonable amount of data. And this is just the error image. So which means we're just looking at the difference to some reference image, and we can see that both results are close to each other, saying that the learning informed model is doing as well as an ab initio model. So which means if you do not know the PDE, there can be some trust, or the ODE, there can be some trust in using a data-based method only in order to still get a good result. Now, what we have done in this first step is look at the sort of general optimization framework where we have learning informed physics constraints. So we have 2 approaches where we either learn a constituent and believe in a solution process which is known either analytically or numerically, or we try to learn the full solution map, and this appears to be a side constraint of the overall optimization problem. We did also the analysis and also an algorithmic framework using a specific semi-Newton type SQP with inexact subproblem solves. As I have said, we learn also in the second example, operators between infinite dimensional spaces. This is a topic which still is worth being further explored, I'm sure about this. And what is ongoing right now is that we try to shift to non-smooth physical models, because very often we see that people use non-smooth activation functions very commonly, but also maybe very leisurely without thinking about all the consequences coming from the non-smoothness, because my control to state map would immediately be non-smooth, even if the original map would be smooth, and this causes some difficulties, as we all know. Of course, we can also think about more general physical operator learning schemes. So for one instance could be, for instance, if you have a 2-scale problem where you have a coarse scale and a fine scale, and for the coarse scale problem, you have a kind of solution process at hand. For the fine scale, you don't, but doing some approximation can never be good enough using, for instance, finite elements or finite differences in order to be accurate. You may want to use a neural network-based approximation for the fine scale and try to complement it by connecting it to a coarse scale quantity, which then is at hand through the unknown solution process. This gives rise to a similar framework as the one which I have shown you today, but still more analysis is needed. Of course, as I've said, also the interplay of the learning problem and some optimization routine outside using the learned quantities inside is still a delicate task that needs to be done. So in a sense, you wish to inexactly solve the learning problem early along the iterations and get only more accurate as needed, given the main optimization task. And of course, there are many other aspects of learning. I give you some glimpse on 2 scales. It could be multi-scales. That's what we see in many applications. And of course, many more ideas and aspects connecting learning and optimization. With this, I guess I'm at the end, and thank you very much for your attention. Thank you.
Thank you very much, Michael, for a very interesting talk. So it is time for questions. Are there questions? Let me ask the first question. So you mentioned no smoothness. Of course, there can be no smoothness in the solution operator or in its approximation because of activation functions. But how meaningful would be no smoothness in the objective function? I mean, in the, let's say, in the misfit function, to make things even more complicated.
Yeah, I mean, there are, let me just go through the problem. So maybe if you look at this problem here, I mean, as you say, if you replace the pi by pi n and the neural network is non-smooth, even if the original solution map would be smooth, you get the typical difficulties. The control to state map is non-smooth. We have to talk about directional or Hadamard differentiability. You wonder what kind of stationarity principle is at hand. You no longer have KKT type conditions necessarily, but you may get something like B stationarity, or maybe you can, depending on whether you can characterize the solution, maybe explicitly also arrive at strong types of stationarity. This is all something which then needs to be shown. And of course, this is a bit delicate because if the original problem was a smooth one, you more or less replaced it by a very complicated problem just by bringing non-smooth activation functions. So better think twice, so to speak. But there are problems which are non-smooth, as we know, and then it might be worthwhile to explore the non-smooth pathway because it fits the problem scope. For instance, if you have a variational inequality, the solution map from a control to a state would be just Hadamard differentiable, and then it might make sense to keep this level. For the objective, of course, there are 2 ways how non-smoothness at least can enter in a meaningful way. One aspect could be through the control process. For instance, if you target the sparse control, let's assume you would like to distribute actuators at sparse locations in the domain omega, then one way to operate here is to take measure valued controls. Then you would replace this maybe Hilbert space norm squared by the measure norm, but nothing squared, just the measure norm, for instance, the total variation of the measure. And then you have a non-smoothness in U. If you wish to think generously about it, then you would say this is like an L1 type of control cost here. But of course, because of some functional analysis properties for P, you would end up with a measure quantity there. And for the first term, it very much would depend also on the underlying information. In inverse problems, of course, the point is, if you have a Gaussian error behavior, let's assume you have some pure or some ideal data G, but the measurement data, some pure data G hat, but the measurement data G is spoiled by noise. And let's assume this noise is Gaussian randomly distributed, then the maximum likelihood consideration leads you to the square norm here. But if you have impulse noise or other types of imperfections in G, you may want to use, for instance, some L1 type error term here. And this might still be very meaningful because for quadratic ones, obviously, you're very sensitive to outliers in the data, whereas for non-smooth terms here, you're typically more robust with respect to outliers. And so there are many reasons, depending on the underlying problem setting, to introduce non-smoothness in the objective, but also in the constraint map.
But then you would need an algorithm able to solve a non-smooth, non-convex problem.
Yes, I agree. And then, of course, it would depend very much on the underlying equation. If the equation would be simple, which, of course, as soon as you introduce learning, it might not be right away. But let's assume you have a simple equation. You could think about dualizing the problem, and this might give rise to some constraints in the dual, whereas the objectives may look nicer. But of course, if the problem is non-convex, then of course dualization is a delicate process in its own right, and then this might not be helpful. But I agree. As soon as you have a specific non-smooth objective, you have to use a different solver. But if you think about, for instance, the measure norm example, the L1 norm example, you would have a very structured non-smoothness, and you may be able to tailor your solution method to this. I mean, you and many of you have worked on methods using Prox type regularizations. You could also want to dissect an L1 norm into active and inactive components, depending on whether you sit on one of the slopes, -1 or 1, or at 0. So there would be many ways to tailor a method now to the specific problem setting. But in general, you're right, you would need to use a kind of non-smooth solver then, which may be delicate in its own right. Even if the objective is smooth, if the mapping U onto Y gets non-smooth, we already talk about a completely different solver class we need to choose. So this is why I was so keen on distinguishing between the smooth and the non-smooth activation functions.
Thank you. Further questions? So we have a question in the chat. Can you read the chat, Michael?
Yeah, I'm trying to.
So the question is if you can use Newton iterations for training the network, neural network.
Say it again, whether I can use.
So the question is there any possibility to do Newton iterations for training through neural network?
Newton iterations.
Newton
for training.
Newton.
Yeah,
Newton.
I mean that's a good question. Of course, first of all, it would depend on the structure of the problem, but of course on the size of the problem as well. So I wouldn't rule it out, but what is very common, of course, these days is that you use stochastic gradient type solvers in one way or another, or some ensemble type solvers, which can cope with very large dimensional problems somehow. But I think you can certainly try to bring in second order elements if feasible, given the underlying structure of the learning problem. Of course, if you want to have a full Newton method, it would very much depend on the size of the problem. I think for the sizes which we looked at, it's still feasible. But for other ones, and you may need to stabilize maybe because you have a non-smooth, a non-convex problem to handle in general. But yeah, but there are other ways to go as well. I mean, we thought a bit about the multi-scale type solvers where to try to understand the network and try to also use coarser and finer versions of the network in order to solve an optimization problem by having a kind of prolongation and restriction operation similar to what we know in multigrid. So I think there are many ways to go. I wouldn't rule out Newton, but I would say it has also to be done with some care depending on the underlying problem structure and size.
Thank you.
Here I see chat. There's a second chat question. It hides on the top. Wow, okay.
Are there other questions? So I have a further question. So you used in your technical consideration the derivative of the objective function. So after let's say rewriting the problem as an unconstrained problem. So
what do you
but
mean?
this means that you would need a derivative of the solution operator. So
yes.
So what would be this derivative?
No, I mean, in our case, it's sort of unsuspicious because in the first example, the mapping N would replace a mapping F. And since N uses smooth activation function, it's sort of a smooth map. It has a specific structure, even because it's activation after affine transformation and so on and so forth. So in that sense, it has a specific structure, and we have a general result saying, if you then plug it into the PDE and solve the PDE by the typical means, the control to state map has certain smoothness properties. Of course, if I would have used a non-smooth activation function, this would immediately have been gone, even if the little f function would have been a smooth function, because of the choice of using non-smooth activations, you walk into a different realm, so to speak. And then you have a kind of Hadamard derivative typically only at hand, which you may still hopefully characterize to some more extent because of the specific shape of the mapping N. And this can be done. This is something we're working on right now. But yeah, you're in a different framework, and we do no longer talk about classical KKT stationarity band.
Okay, yes, thank you. But then, okay, then I have to ask for a question. So,
yeah,
then you are solving the problem which you can see now on the on this slide. Yeah. So which would be a smooth problem, and
yes.
then you are still solving it by using a semi-smooth algorithm.
Yeah, because we allow for constraints in U. So C admissible in, for instance, is a box.
Okay. Okay.
And then you use a complementarity, an NCP function to replace the complementarity system by a non-smooth equation. And even if you do an SQP ansatz, the constraints remain in a shifted fashion because you have then UK plus delta U, so to speak, being between bounds. And then you still have a non-smoothness coming through this. And we find that the semi-smooth Newton solver does a very good job in solving the subproblem, even to high accuracy, but sometimes not even needed.
But then, Michel, what speaks against, let's say, projected gradient or projected Newton?
Well, not much. It's just, in my experience, the QP solver is very fast. If you use the semi-smooth Newton for the QP part, we would even have a mesh independence result at hand, which means if you discretize the PDE from a certain discretization fineness and to finer meshes, you would have essentially always the same iterations or the same kind of speed of approximation. Of course, you could do projected gradient type structures. Maybe they would not be as quick as a Newton type structure, in my opinion. Of course, there are many ways to go. I mean, it's just we have very successfully used semi-smooth Newton methods, and they seem to work very well. And we even attempted to use semi-smooth right away for the KKT system, just as a non-smooth system. And it works beautifully, even if you do a very, how should I say, a very coarse type of globalization, which would be more heuristic than analytic, so to speak, or guaranteed. Even then it works well, but to be on the safe side, we did this as semi-smooth Newton for the subproblem, QP, SQP type solver with inexact line searches in order to have a guaranteed convergence result in the typical sense of nonlinear program.
Thank you. If there are no other questions, then I'd like to make a final comment. So, I mean, I found let's say the future topics you are proposing actually very appealing, in particular the ones related to the non-smooth case, and then in connections to some globalization statements which you have in high-dimensional spaces by using critical service property. Then the interesting question is how to extend this property to a setting which is not anymore high-dimensional, in order to, let's say, to replicate or to extend results we have in high-dimensional spaces. And there are attempts. There is a critical service formulation in spaces which are not high-dimensional. And the question is how to guarantee this property and which spaces for which functions, in order to prove globalization of algorithms. So,
I mean, this is a very interesting comment. So what we are doing right now is we are trying to explore structural properties when we use, for instance, ReLUs. For the sigmas, you still have a very specific structure, but of course you have non-smoothness, and you can show that the solution map has certain Hadamard type properties, and you can characterize the derivative, and you can get the kind of adjoint system out of this. So we have not yet thought about the algorithmic component of this. We just try to understand the analytical implication, because sometimes you have problems where you just do it without knowing better, maybe, and sometimes you have problems where it really pays off to use a non-smooth activation function because you get sparsity of the network or you have better approximation quality. But then I guess we should come back and talk to each other, because I think that sounds like a very interesting step, having a robust method for giving you a kind of strong stationary or some strong stationary point, because we believe that we can characterize the derivative so that you have strong stationarity at hand. Whatever strong means now, it's not an MPEG. It's a system with a non-smooth equation which you can characterize. You can look at the reduced problem. You have a non-smooth object, as you mentioned correctly. You have a non-convex, non-differential objective over maybe simple constraints, but that stationary would be kind of P stationarity, but using a dual concept, I would call it the kind of strong stationary principle. although it's not necessarily immediately an impact, so to speak. Yeah, so I think that's an interesting direction to go, Rado. So we should definitely talk about this.
Very good. So then, Michael, thank you very much for a very nice talk, a very nice discussion. So we stop here. I'd like to thank the participants for being with us today. So we will post the slides and the video on the website of our seminar. And I'd like to announce that our next speaker will be Marco Lopez from the University of Alicante. So thank you, Michael, again for a great talk. Have a nice week. See you next Monday.
Thank you very much, Rado, and thanks to the audience for joining in. Thank you very much. See you soon. Bye.
Thank you. See you.
Bye.